Okay, this is John Gonder for Wireshark, and we're going to take a quick look at 3 Nmap scans. And first, of course, I want to make sure you've watched the IP addressing basics video that I emailed you about. And you will remember, because I know you've already looked at the preparation videos that I sent you before, this one in particular, which goes over the use of Nmap, and especially with regard to SYN and Connect scans. There's a lot on Nmap on ACM to read and go more deeply into it, both with books, courses, labs, and videos there. This is a very deep subject. It is very strong, very useful, and we're only getting just a teeny little bitty taste of this. The Nmap cheat sheet, which is in the Week 6 Lab Docs folder, has a lot of cool stuff with various scan options, a couple of which we'll use here. Timing from sneaky, very slow, maybe won't get seen, to polite, normal, aggressive, paranoid, and insane, which we'll talk about a little bit in a minute, a couple minutes here. Of course, our usual way of working, of course, is to close unneeded apps, run Wireshark, do what we're doing, in this case run a scan, stop and save that, and then we can start to ask some questions. What do we think happened here? Of course, we already know, since we're looking at a scan that we initiated, what supposedly was going to happen. And given that scan, given the information that comes back from that, what can we see? And then what do we think it means? And of course, we are learning what it looks like when somebody does that to our network. This kind of practice allows us to see what kind of patterns, what kind of activities indicates that someone is scanning our network in one way or another. The ZenMap front end for Nmap actually is a client-server architecture, and if you look at it closely on the Mac here, I tried to take a screenshot to show there are 2 apps actually running. One is the client app, which calls the server app. I'm running it locally. I could actually run that server remotely somewhere where maybe I wouldn't be seen, and I can control that from a distance. And that's an aspect of some of the kinds of utilities that might be used by a hacker or might be used by penetration testers, that we can have a server which resides somewhere else. Now, scan number 1 here is going to be just a simple ping scan, the kind we might use just to discover what devices are operating available within an IP range, and then we might zero in on some of those in a particular way. Nmap small s capital P, and then the target, or in this case a range of IP addresses. Now you know what this means from that IP address basics video. I'm defining the local area network that I have here. I check to see what I have by ipconfig/all in the case of Windows, or ifconfig. EN1 is my local area network interface card here on this particular Mac, and I can see I've got an IP address of .23, the net mask, which is printed in this application not as a decimal number but as a hexadecimal number. That's 0x, means what follows is hexadecimal. FFFFFF00, which corresponds to 255.255.255.0. All ones in the first 3 octets and all zeros in the last octet. And then, of course, that means the broadcast address would be what? The network number and all ones in the host field. So in order to scan my local network, I need to put in what my local network address range is. And so I've got ZenMap running here, and I'm going to go ahead and type in what I want here, which is I want a SP scan of 192.168.0.0/24 and go ahead and start that scan. And I would be capturing with Wireshark and then save once we're all done. And we're done. And so we see, here's our report. We see a couple of addresses currently running. Let's go over and take a look at Wireshark, and I'm going to open up my saved file, which I named Gondar Nmap Ping Scan on the 192.net. And let me take a look here under protocol hierarchies just to see what I've got here. Now I can see bottom right I've got 740 packets. They're all currently displayed. Actually, that's going to be maybe covered up by my picture. I have to make sure not to do that. They're all Ethernet, IP version 4. There was a couple of UDP packets, MDNS, a lot of address resolution protocol, a little TLS. You apply that as a filter, and so we can see this was actually a 17net, which I recognize as a Class A address owned by Apple. So this was some stuff in the background application working. It's not what I was looking for. Now, I could try to apply a filter here. Now, I could try to filter by IP address. Of course, the source of all my packets is going to be 2.23 here. And I don't necessarily know the destination because I specified a range. Well, I saw here in statistics that the protocol hierarchy, that there was a whole lot of address resolution protocol. Let's take a look and see what that is. Go ARP. And then what do I see? Well, the process of enumeration, saying, what devices are actually on here and might actually be responding and doing something, one might expect that we would see destination IP. Well, this is a broadcast. This is an ARP. And let me just right-click here. And I don't have a column for the source MAC address, and the destination MAC address we can see here is FFFFFF, right? Expressed as hexadecimal. In binary would have seen what? All ones. So what's happening is my local device, which Wireshark knows is an Apple device, that 1314:7D-DA is the organizational unique identifier of Apple, is sending out a whole bunch of ARPs. And the ARPs are saying, let me move this over here, who has .1? Tell me. Who has .2? Tell me. Who has .3? Tell me. So does this look like somebody scanning our net? Yeah, they're calling out individually to each individual device, and the devices that are currently up then, because it's ARP, will reply. Hi, I'm .1. Hi, I am .8. Hi, I am .9. And that's where I am. So that's where, and hi, I am .13. So, .13. So, 71, who's 80, is 87, 95, 105. So we've got then what? We've got a call out, we've got a shout out to every individual IP address in that range. So this is what Nmap is doing when we tell it to say, well, do a ping. It's not really a ping, and it's a ping in as let's see who's there. Let's see if we've got ICMP. No, none of these are ICMP. So that's pretty straightforward. And we saw what it was that Nmap did, and we can see what kind of information is brought back with that simple scan. So that was ARPS. If I was writing a report, that's what I would probably talk about with this particular scan. I checked my system to see what network I was on. I did a enumeration scan of that address range, and that's what I found. Now I could have a display filter. Actually, no, I'm going to get rid of that because we didn't make use of that. Okay, so let's go and talk about scan 2, which would be a TCP scan -S, capital S, and known as a half-open scan. So I'm going to get that ready here, Nmap-S, capital S, and my IP range. And I'm going to then get ready to capture with Wireshark. I'm going to choose my wireless network. I'm going to go ahead and start that. And now I'm going to start my scan and see what I get. Got a lot of packets happening. The scan is done. Nmap reports 5 hosts were up. And on this one, the .1, these are the ports that were open: 5380, 443, 5000, 5001, 8080, the alternate HTTP. I'm going to go ahead and stop here, and then I can save that as go under Nmap scan. And now let's take a little look and see what we can see. Well, there's a whole lot of red stuff here, isn't it? Where there were resets. I'm going to hide this, or actually remove that column, and I'm going to move this back over where it belongs. And let's start taking a look. Well, right off the bat, I've got what, Dropbox, so that's not part of my scan. Local thing is sending out a broadcast. And then there's ARPs that are coming from my router. And then we got ARPs that are coming, you know, who has one, who has two. Who is sending this? Well, let's take a look at that. Highlight that packet. We can see that the Ethernet source is an Apple box. That's the same media access control address we saw before. That's my Mac Mini here. So there were ARPs coming out from that scan, and then farther along, we started to see SYN requests from there to .1, looking for port number 6566. That's interesting. I'm just going to sort by destination port here, just for fun. And then I'm going to click one more time to put the highest number up. So the first 10,000 ports. And it's interesting actually to see that Wireshark doesn't really sort numbers correctly. here. Not quite. But now we got a reset here, didn't we? We sent a reset. Let me go ahead and follow that TCP stream, which will pull out just the packets there. And so there was a SYN, a SYN-ACK, and then a reset. Let's put these packets in order. First was a SYN request to .8, and then .8 on that port, the destination port, was 9080. Actually sent back and said, oh yeah, I've got somebody listening on that port. The operating system on whatever device that was said, I got somebody listening on that port and they're willing to talk to you, SYN-ACK. And then I don't follow through. That's why it's called a half open, because we have that SYN request from me that's acknowledged. So that half of the TCP highway is open. Then that SYN comes back to me, but I don't acknowledge it. So both sides of the highway are not open. Instead, I send a reset saying, I don't really want to talk anyway. Let's look a bit more closely, though, at this particular SYN packet. Let's see what we got. We're used to seeing what? We're used to seeing that there's TCP options. And here I'm seeing there's a SYN flag. And the Windows 1024, which, as you remember from Chris Greer's video, he knows that this is really small. This is not really normal. Normally, that's not a big enough bucket on this end to actually even hold one entire packet. So this is kind of bogus. And then there's a maximum segment size, but we don't really see anything else. We don't see, does it do SAC or not, selective acknowledgments. We get a SYN back from the other side, and this side has a usable size window, and it has a segment size, and then it has, yeah, there we go. But then I say no. So this is really just what, a half open connection. And so then what we see there is all of these ports that are being tested on all of these machines. More often than not, well, very, very often, we just get an nobody listening on that. There's no application running here on top of this operating system which is capable of conversing on that port. So we did see, as we saw in the Nmap report, we did see for this .1 there were a number of ports that were open, and so if I actually, let me prepare a filter but change that to .1, if the source is .1, so .1 said no to all of those ports, but it did say yes to port 5000. Do we know what that is? Doesn't sound like a very standard port, but that .1 is my router, so that could be something that is unique to routers. I'm going to go and take a look at that, and that could be something for me to talk about. And when I'm taking my notes here, I'll start to make notes about things that I might want to talk about. So that's a half-open SYN scan and what things look like. And of course, in the options we saw, there's some things that are kind of non-standard there. It's not actually asking to talk with only a 1024 size bucket on this end for a window size. Well, let's take a look at a third kind, which is a full TCP connect scan using -ST for a full connect. And I'm going to make that a little bit less of a range. Well, or maybe not. Let's just make it -T, capital T, and get ready to capture. I've got that saved already, so I can capture options. EN, start that, go here, start my scan. Have a little coffee or some water. Now, actually, this is really interesting. In other words, I'm capturing a lot of packets, but I actually still have a display filter showing. So only those packets that fit that filter are showing up here in my graphic user interface for Wireshark. So I'm seeing where there were requests for various ports to .1. Well, again, 53 was open, got a SYN-ACK back. All the others, nobody listening. On that port, there's no application above layer 4 which is capable of speaking on that port, so I'm going to send you a reset. I'm going to clear that filter just to see, yeah, in reality I've got a ton of different packets here. And we're still going. I'm going to pause and come back when that's all done. And in actuality, I stopped that and I went back and I started that again with the -F, which should check only 100 ports because I forgot to do my math. That was going to be what? 255 addresses, 254 addresses without the network and without the broadcast, times 10,000 ports. A lot of packets. So this -F should finish up here a whole lot faster. Well, and again, this has taken quite a while, so I'm actually going to cancel that scan, and I'm going to stop this, but I'm going to save this out, and I'm going to call it Gondor-ST192net part scan. And I can see that I am, let me just follow this TCP stream here, sending out a request to .13 for port 1723, and he says back to me, nope, ain't no application here running above layer 4 that's able to listen on that port. Well, if you remember from one of the videos, there is a way to filter on, was there a complete TCP conversation setting up, and if that value in that space was 39, then we can filter on that. And let me go here and filter. I filtered on TCP completeness equals 39, and that shows me, and we can see here where there was a request. Destination port 80, synchronization request, and from .1 from port 80 back to my local ephemeral port used for the request, an acknowledgement of my SYN request and a SYN also. So there is a application layer process working at port 80 on this IP address, and I went ahead and acknowledged that, but then I reset that. It's interesting that it took me right about a second to do that reset, maybe because there was a lot going on at the same time. And then here again, I got a hit on port 8080 with .1, and .1 sent back a SYN-ACK saying, yes, there is an application process running above layer 4, 5, 6, 7 on port 80 that's willing to talk to you. And .23 says, oh, okay, cool. But then, you know what? I really don't want to do that. Interesting, notice that we also got then a reset back from .1. That's interesting. So on and on. So here are the occurrences in which we were able to, in this scan, do a complete connection. Notice in this instance, .9, let's see, what is .9 anyway? Let me close that. .9, there was a SYNAC from .9 on port 49154. We might have to look 49154. Make a note there. I might look and see what that is. I might want to talk about that. And not only did I get a SYNAC back from them, an IACT, then they sent me a TCP window update, meaning typically, remember in that process when they're first negotiating, the operating system doesn't necessarily use up a lot of its storage space, creating some huge bucket before we even know we've got a pipeline to the other side. That's very often why you'll see a TCP window change. Once we have that SYN, SYNAC, and ACK going, the server then, if it's going to be accepting things, is going to create a larger bucket for receiving things. If it's a client that's going to be receiving things, it's going to create a larger bucket for receiving things. So we're not sure what this process is here, 49154, port 49154 on .9, but I am kind of interested to see what that is. Well, that's destination was going to my Apple. The source port was this. Now, I note that Wireshark does not have an entry in its MAC address OUI database to be able to put a name to F6B3D6 as a company creating this particular network interface on this device. So we're not sure what this is. This is actually a perfect example of something. This is something unidentified on the net. If it didn't occur in our baselines before, we might want to further investigate. I'm not sure what this is either. I thought Wireshark actually knew the OUIDs, recognized the MAC addresses of all the devices I have, my Roku, maybe it's my washing machine. Who knows? We'll have to go and look at that. That's another thing. No organizational unique identifier. Actually, it's OID, they call it now. I first learned it as organizationally unique identifier, OUID. So interesting stuff. So this is the full connect. By the time we're done here, we've got SYN. We want to talk one way. SYNAC, yes, we want to talk the other way. Yes, I'll acknowledge that. Now we have a two-way pipeline, which then I proceed to tear down a second later. Now that's interesting. Notice fairly consistently that teardown was a second later. One of the ways in which we can conduct, or someone can conduct against us, a denial of service attack is to essentially use up all of the resources of something like a server. How might we do that? Well, I do a half connect where, yeah, I want to synchronize with you. The server sends back SYNAC, and I just don't say anything. Eventually, the server will say, geez, nobody's answering. I'm going to free up the resources that would have been used to create that connection to connect with somebody else. But if from a whole lot of different ports or a whole lot of different spoofed IPs, I do the same thing over and over. I can fill up all the available chairs in the waiting room on that server. And now anybody with a legitimate reason to connect to that server can no longer get on there because there's not enough resources. A denial of service attack that way. Same thing, I could do a full connect here because the server might much more quickly free up its resource if it never hears back a SYNAC from me. But if I go ahead and do that, but then never say anything, SYN, SYNAC, ACK, oh yeah, now we're open. but then I never actually send a reset, that timeout on the server is likely to be considerably longer, makes it easier for me to tie up all its resources, and then nobody can actually get on. They get a busy signal. So there we go. There's 3 scans. Now, there was an Nmap profile there in that in the week 6 lab docs that we didn't actually make use of. And one of the reasons was the Nmap profile itself did not seem particularly useful. It was just kind of a normal group of things, and in actuality, my basic TCP all columns profile is a lot more useful. However, notice how useful this particular filter is, this display filter. What I might do if I am consistently going to be looking for Nmap, what are some of the characteristics of Nmap? Well, it's got a small window size on the SYN request. So I could create a few filters and have them be buttons with a drop down for like Nmap characteristics, and make myself a copy of something that has a whole lot of stuff already set up, like TCP all columns, calling it mmap find or something, and create a few buttons with things like completeness is 39, window size is very small, and like that. So I can start to create a custom profile for myself for looking for Nmap or looking for the characteristics of some other scanning utility. Well, let's go ahead and do a bonus. Well, a bonus that I've done already is to scan using a Christmas scan or Xmas scan, nmap-sx, and I scanned nmap.org, the ScanMe device, and this is what it looked like when we got done. And let's go take a look at that inside Wireshark. Let's see, I should have the open the recent. I think I've opened too many in the meantime. There we go. So here's my Xmas scan. So when we're doing penetration testing, one of the things that we can do to identify operating systems or identify other characteristics is to send something that is abnormal, that is not normally seen. Do we want to do that? Is it safe? If we do something like send an insane scan rate to a production server or a database, are we going to crash that puppy? If we do something like a Christmas scan or some other format that is not according to a protocol, will that device be able to deal with it, either ignore it or be able to deal with it in some way that does not affect it adversely? Well, why do we want to do that? What do we have permission to do that? Was it in the contract that we have? Are we pen testing? Are we stress testing? There's various reasons why to or not to use particular kinds of scans or particular kinds of approaches for a device or a network. If we are stress testing something that is not a production device, not currently in use as a production, that is a fairly normal thing to do. Yeah, we think this all works, but say before we buy one of these, let's stress test it and see whether at maximum usage it actually craps out. Am I pen testing stuff? Or am I just a hacker and I just want to see if I can crash stuff by going insane with stuff that normally is never seen and may very well not be dealt with nicely by the device that I am looking at. Well, here's the result of our Nmap scan on scanme.nmap.org. Well, I can see I've got some stuff here to Apple 17. Whatever. Well, let me find. I remember that 45 was the IP address of ScanMe, so I'm going to prepare a filter. The destination is 45, and actually I'm then also going to prepare or selected. So if the source or the destination was 45, then I can filter on that, and I can see instead of 2163 packets, I've got 2008. And I'm going to hide a couple of columns here. Source, destination, frame length, protocol, ICMP. So we can see the first thing that happened with Nmap was it did a ping. Now, sometimes if Nmap can't get a response from that, then it'll quit there and not do the rest of the scan. And it may not get a response because ping's ICMP is being filtered at the other end, even though the device itself may be up and would be responsive if we did the rest of the scan. So that's where some of the options you'll see with Nmap are to just don't bother doing a ping, just try to go at it and see what you get. Well, we can see here that we're looking for blackjack, interesting. We're looking for a reaction on POP3, on 110, on 135, 139 net bias, on HTTPS 443, 995, another email port, standard port. And in each case, why do we call this an Xmas scan? Well, because let's take a look at some of these. Here is a packet coming from .23 to 45. And what do we see about that? Well, here's the source and destination MAC address. That looks normal. IP. Time to live is 37. Well, not very high, but that's okay. Source, destination, IP. Source port, destination port. Here's what we see. Christmas scan. The urgent bit is set, meaning don't wait for there to be a full bucket before you send this up to the application. Send this piece of information, as small as it might be, to the application right now. Push. Yes, push that right up to the application. But wait a minute. I'm sending you the fin bit, which means I don't want to talk to you either. So I want to talk to you. I got something to send you, but I don't want to talk to you. I got something to send you, but I don't want to talk to you. Doesn't make sense. How does the other application deal with that? Well, we'll see. Maybe gracefully, maybe not so gracefully. So this is what an Xmas scan, Christmas scan looks like here. Is we've got an unusual configuration of flags, ones that normally would never be set all at the same time. Now, you can actually decide individually, manually yourself within those subtle settings of Nmap that are not just standard checkboxes like -ST, -S. I could set for all of these to be 1. Of course, that would never, ever happen. And remember, we want to be prudent in what we do unless we really want to push the other side and see what we can do. So if somebody's sending us packets like this, we know they're not our friend. They are definitely working on something. They've got an agenda of some kind at the end. So the Christmas scan, unusual flags. And so we would definitely want to talk about that. Okay, so what's the bottom line here? Well, the bottom line is we looked at 3 Nmap scans plus a bonus. And you should have already been watching the IP addressing basics in the Chris Greer video, look for Nmap on ACM. If you have any interest in really learning this stuff, there's a lot more to it than just our little quick look and our quick look using the cheat sheet. We used our standard way of operating. We close extra apps, run Wireshark, run stuff, stop and save, and then ask some questions. Nmap is a client server. The ZenMap front end is a client server system. We ran a ping scan. We ran a half open SYN scan. We ran a complete connect scan. And then we had a bonus Christmas scan, which is one of the kinds of things we might see if someone's really doing some funky stuff, sending us a set of flags that should never occur at the same time. So there you go. Hope that gives you some more things to think about and help you see that there's a lot going on in there, but it's not that hard to see. Not that hard to see. So enjoy, and we'll see you on the net.